In this unit, we're going to start looking at exponential functions, their derivatives, and some applications of those. Just some reminders, exponential functions are basically two types. There's growth, so things that grow from left to right. So for example, y equals 2 to the x. And there's decay, so ones that get smaller from left to right. Those are usually fractions or negative exponents. Because a negative exponent does the same thing as creating a fraction. Okay, just get ourselves started on this topic. We're going to learn about a new number today. So I've got a series of numbers here, and I've got an expression for you. I want you to evaluate this expression using our series of numbers. So for example, let's say n is 1. Using this expression, I end up with 1 plus 1 over 1 to the 1. Or in other words, 1 plus, oops, not 2, 1 plus 1 to the 1, which is 2 to the 1, or just 2. If I try the next one, we'll get 1 plus 1 over 2 to the 2, or in other words, 1.5 to the 2. And you're going to need calculators for this lesson, so make sure you have your calculator out. And 1.5 to the power of 2 is 2.25. We try the next one, 1 plus 1/5 to the power of 5, in other words, 6/5 to the power of 5. We get 2.4883. So you might notice so far that as our numbers get bigger, so do our values, but they're not increasing by a huge amount every time. We started at 2, and we're only up to 2.48 so far. Okay, we'll make it bigger again, see what happens. And there is a pattern here. That's kind of our objective, is to figure out this pattern. If we try n being 10, we'll get 2.5937. Okay, so we doubled it, and it really didn't change all that much. What happens if we multiply by 10? 10 times as big. What do we get? Well, if we try n being 100, you should get on your calculator approximately 2.7048. So again, it got bigger, slightly, like 0.1 bigger, not very much. What about 1,000? Okay. If we try that one, we should get about 2.717. And obviously there's more decimals behind this, but approximately that big. So it grew, but just barely at this point, right? Even though we made our exponent really big. What if we tried 1,000,000? 1,000,000. One more zero. To the power of 1,000,000. If we put that into your calculator, you should get 2.7182 approximately. Now, what if we go one more step? Infinity. Think of the biggest number you can possibly think of. And if you make that as a fraction, to an exponent, the biggest number you can think of, the biggest number your calculator can handle, if you punch it in, you should end up with 2.7182, and obviously a few more decimals after that. So what do we notice? As we got bigger and bigger and bigger, our numbers started approximating the same value. And this is a really special number. And the number we just figured out, that idea of 1 plus 1 over n to the n, which can be approximated to 2.718, is a special exponential function that we call y equals e to the x. Okay, so e is a special number. Its value is approximately 2.718. We call that Euler's number. And we use it, and there's actually a button in your calculator if you can find it. It has an e to the x button. Okay, it's a special number. We also call it the natural number. Okay, and the idea of e is it's determined by the limit of what happens as we approach infinity. And the closer we get to infinity, the closer this number comes out to, at 2.718. Okay, so when we started at 1, it wasn't that close. We had a value of 2. But the bigger and bigger we got, the more and more we approached 2.718. Okay. The nice thing with this number, this natural number, is it is a special exponential function, which means that all the exponential function rules work with it. So exponential functions involve exponent rules. They can be used with logarithms, because the logarithms are inverse functions for exponentials. Okay, so you might recall from last year, a function of being 2 to the x has an inverse of log 2 to the x. It undoes what the function does. Okay? In much the same way, E has its own special inverse. So if we come across the function e to the x, okay, which is really just the number 2.718 to the power of x. That's all that really is. And there's more dots here, obviously. Okay, it's just a special one, which means that there's a function which we could call log of 2.718x, or, if you will, log e to the x. But instead of doing that, we use something else called a ln. Okay, so whenever we come across a log e to the x, we're going to replace that with a ln, a special natural logarithm, the inverse of the e function. Okay, so that's a lot of stuff there. We'll go through some examples, see how this works, okay? So one of the best examples of how this works is the idea of finance. E stands for the idea of not doubling, not tripling, not increasing by percentage. It stands for continuous growth, always constantly increasing. Okay, so if we go back to finance and what we looked at last year, we talked about compound interest. You might remember this formula. If not, nothing in the world. We'll go back over it again when we get to finance. For now, we'll use it. That would be our standard function for growth of money that we put in the bank, our present value, after a certain amount of compounding periods and a certain amount of time at a certain rate. Well, those calculations are done at the end of every week or month or quarter or year, depending on the compounding period. Continuous growth, rather than being calculated at the end of a certain time period, is calculated continuously. That's how we can use E. So we can take the same kind of equation where we have a future value, a present value, but instead of having a 1 plus growth, we have an E growth. And the only trick here is you have to figure out your rate as a decimal and N is your number of years. So quick refresher. We've got $1,000. That's our present value. We're going to go for 10 years. That's our N. 5%. That's our R. And we're going to compound things quarterly. That's our K. How much money is this going to be worth down the road? Well, it'll be 1,000. 1 plus R over 100 quarterly. Quarterly means 4 times a year. 4 calculations. We're going to do it 4 times a year for 10 years. You can punch that all in your calculator just the way it looks. Maybe think of the exponent as a 40, makes it a bit easier. And it should come out to approximately 1643.62. So you earn $600 in interest. Okay, the more often we compound things, the faster things should grow. So we take the same equation, but do it monthly this time. So our $1,000, 1 plus, still 5%. We're going to do it 12 times a year, monthly, times 100, to the power of 12 times a year for 10 years. Well, this time, the only difference we've done is calculating more often. We've got ourselves a little bit more money. We've earned almost $2 more in interest, or sorry, $4 more in interest just by calculating more often. We haven't left it in longer. We didn't put more money in. We just calculated more often. And then if we take the last one, the continuous growth, our future value will be 1,000. E, 5% as a decimal this time. Okay, make sure it's a decimal for our 10 years. So what happens if we make this calculation even more rapidly, all the time, continuous growth? Okay, not a different amount of money, just more often calculations. Well, again, we have just slightly more, but the nice thing is we haven't actually done anything different. Just let the calculator do more operations for us. By doing it that continuous growth, we've made almost $5.10 more than we would have just by calculating it once a month, or sorry, quarterly. Okay, so it's just a slight small example of how we can use E as continuous growth. Okay, a little bit about the function itself. E is an exponential growth curve, like 2 to the power of x, except for ours is going to be e to the power of x. So you might recall from last year, exponential functions, our domain is always all real numbers. They go left and right theoretically forever. Our line could keep going this way, and it's going to go up, but it's actually getting wider at the top. The range, these have asymptotes. They never hit the y-axis, so y is always greater than 0. And that can change, I suppose. If you add in an asymptote over here, like a plus or minus, that would move the graph up or down, but we're not going to have that in our functions. Here are zeros. Well, if we don't hit the x-axis, we don't have any, so not applicable. The y-intercept should always be 0 and 1, because when I put in x equals 0, which we always know works for y-intercepts, e to the 0 acts like any other exponential function, comes out to 1. These functions are always increasing. Always, always, always. They're continuous growth. Okay? They're also increasing at an increasing rate. So that means they're concave up. If you think about your tangent, it starts off here, then here, it's getting steeper, then here, it's getting steeper and steeper and steeper all the time. Okay, and asymptotes, yes, we mentioned that already. We have one. It's a horizontal asymptote, and its equation is y equals 0. Okay, let's look at the ln function, the inverse, the diagonal reflection, if you will. You may remember that from grade 11, the diagonal reflection. That's really what a ln is, which is also a log function, just a special one, right? We said this is like saying log e to the x. Okay, what's the domain for this? Well, the domain for this one is it's always greater than 0. The range, it's all real numbers. And just to point out this little trick you might recall from last year, inverse functions always go this way. What happens for one happens for the other. Okay, so if the x was all real numbers for domain, that means the range will be all real numbers for the y, and vice versa, and vice versa, and vice versa, all the way down. Okay, they should be opposites or inverses of one another. So just guessing without thinking about it, I should have a not applicable for my y-intercept, which is true. I don't have any. I should have an x-intercept of 1, 0, because it should be the opposite. Which, if I look at the picture, sure it is. If one was increasing, the other should be decreasing. And again, yeah. Oh, sorry. Actually, that's the one thing it's not doing. This is an increasing function still. Sorry, my fault. I was thinking ahead to the next thing. Okay. Exponential and logarithmic functions always increase from left to right. So we're up and up and up and up. But the next one, the concavity, this one is down. Okay? Our tangent, okay, is getting smaller and smaller and smaller and smaller. And the slope of that tangent continuously, so it's concave down. And then asymptotes, it's got 1, it's the opposite one, it's got the x-asymptote. Now, I'm not going to ask you to memorize all these things, it's just the idea where the graph comes from and how we can work with it a little bit. And what we really want to do in calculus is be able to talk about rate of change, derivatives, tangents, those kinds of things. So, if I want to find the derivative of an e function, an exponential one, there's something kind of cool about this one. For the function e to the x, its derivative is actually the function all over again. Now, it sounds a little confusing, but here's what it is. If I have a function e to the x, its derivative is e to the x. Okay, because the reason why is it's because it's got this continuous growth thing. And obviously that would make our life pretty easy if we only had functions e to the x, because you always have the answer. But unfortunately, most of our functions will be e to the power of some other function. And for example, e to the 3x. Okay, this part up here is its own function. So take derivative of these ones. Okay, any function involving e starts off with itself as part of the derivative times the derivative of the exponent. And that's our idea of the chain rule. The exponent comes down, and you take the derivative of the exponent itself. So we'll try some. Determine dy dx. So dy dx. Whenever I have an e, my derivative is itself times, I use dots here a lot, okay, times the derivative of the exponent. Well, the derivative of 4x is just 4. So the way we usually write this is we put the constant out front. There's my derivative. If we try the next one, dy dx, derivative of y with respect to x, the derivative is itself times the derivative of the exponent, which would be 12x. or if you will, 12x e 6x squared. Okay, so these can get pretty messy pretty quick, as you can see. If we try e, you might notice that we have two functions being multiplied. So we're going to have to go to our product rule. Derivative of the first part, that's 4x, times the entire second part, plus the derivative of the second part, which is an e, so times itself, times 5, times the whole first part. For these kind of functions, when we simplify them, we usually try and common factor. So you might notice they both have a 2x in them. And I can divide this by 2x and this by 2x. I also have an e to the 5x in both of them, obviously. If I common factor that out, I'm left with a 2 plus a 5x. Okay. I'll try a couple more. Pause it, give yourself a try, see if you can figure these out. Y equals. So we're going to do dy dx. Okay, a constant in front. We know that doesn't do anything. It just multiplies in. Okay, so times itself, or sorry, derivative is itself times the derivative of the exponent. Or in other words, 18e 3x plus 8. Try the next one. Oh, it's messy. You got root signs in there. Well, we know we can fix root signs by writing them as fractional exponents. So let's try this one. Dy dx. My derivative has to be its entire self times the derivative of the exponent. Well, the derivative of the exponent is 1/2 times 4x minus 11 to the negative 1/2, just for the exponent part, times the derivative of the inside piece. So we got all kinds of mess here. So how could we rewrite this if we wanted to? Well, 1/2 times 4 is going to make the number 2. So we can write this as 2e 4x minus 11 to the half. And we also notice that this piece right here has a negative exponent on it, which means I can move it to the bottom if I wanted to. So all over 4x minus 11 to the half. Or, if you don't want to use halves, you can put those back as root signs. Okay, and last one, quotient rule. Like everything else, we can apply all the other rules to functions involving e. So our quotient rule says, take the derivative of the top, which in this case is just e to the 6x times 6, times the entire bottom, x cubed, minus the derivative of the bottom, 3x squared, times the entire top, all over the bottom squared. Okay, now obviously that's messy, so let's simplify it. What can we do on the top? This is a dot, remember. Oh yeah, common factors. I see they all have the number 3 in them, or divisible by 3, right? 6, 3 divisible by 3. So I can take a 3 out. They all have at least an x squared in them. I got x squared here and x cubed there. They all have an e to the 6x in them. So if we common factor that out, 6 divided by 3 makes 2. And we had an x cubed, we took out 2 x's, so we still have an x. Minus, on the right-hand side, we just have the number 1. All the parts and pieces were common factored out. On the bottom, x to the 6. Can we make it a little bit simpler? Sure we can. We got x's on the top, we got x's on the bottom, so I can cancel these two with 2 of those, and we'll be left with a nice, well, not necessarily nice, but simpler expression. Okay, so there's our derivative for that messy, messy function involving a quotient. 2 more little examples for you. I want to find the equation of a tangent.
Would Greta Musky come to the office, please?
That's one of our big ideas with calculus. We should be able to find tangents. We've talked about tangents today in terms of concavity. Let's find the equation of a tangent. To find the equation of a tangent, we need to be able to do mx plus b. So we need to have a point and a slope. If I want to find the point, I use my function at 1. So e to the 4 times 1. Now e to the 4 is a messy, messy, big, long decimal. So let's not use it. Let's just call it e to the 4. So I have a point, 1 in e to the 4. If I do my derivative of this function would be e to the 4x times 4, or in other words, 4e to the 4x. And I specifically want the derivative at 1. So again, we'll put the 1 in there. And we get that. Well, again, I don't want that big long decimal. So I'm going to try and build my equation in exact form. My slope at 1 is 4e to the 4. My point at 1 is e to the 4 for y and 1 for x. So we're involving the equation with a lot of e's in it, but it's keeping it exact for us, as opposed to big long decimals that we don't want to prematurely round. Let's simplify this. Okay, e to the 4 times 1 is just 4e to the 4. Okay, we can treat e to the 4 like an algebraic expression. It's a number. We can also think of it as a letter at the same time. So we end up with negative 3e to the 4 is b. What's our equation? Y equals m. M was 4e to the 4, x plus b. And b was negative 3e to the 4. So there's an equation for the tangent at the point 1. Yes, it involves a whole bunch of e's. If everybody wanted to graph this, I could figure out what those numbers were. So I'd have an approximate y-intercept and approximate slope. But we weren't asked to graph, we just asked to figure out the equation. So let's leave it in exact form. Right, last thing, how do we actually apply this? Word problems, applications. To do these kinds of things, we have to remember back to last year and logarithms. Because e is just an exponential equation, all the exponent rules work. And similarly, all the log rules will work also because ln is just a special log equation. So sometimes we're going to have to be able to solve problems which have e's in it. To do that, we can take the ln of each side. Much like in the past, we end up with questions like this. We would take the log of each side. That should look familiar. But now we won't have the number 5 here. We're going to have the number e. So we're going to use our ln law. So ln of 2 equals a ln of e to the x. And just like logs, we can bring that exponent down in front. But here's something kind of cool. The ln of e always comes out to 1. So whenever I get an equation like this, I know this piece just becomes a 1. I don't need to include it anymore. So x equals ln 2 in that case, which is something you can find on your calculator, the ln of 2. Okay, so we're going to try one, an example of this. The distance fallen by a skydiver t seconds after jumping is given by this beautiful equation here. It's got continuous decay. It's decay because you have a negative exponent. It's going down over time. Kind of makes sense, right? Eventually you hit the ground if you're jumping out of a plane, but it should slow down over time. I want to find the velocity. Well, we know one of our basic rules is that velocity at time t is a derivative.
Would Mr. Thomas contact the office, please? Mr. Thomas.
Of displacement. Right? Now, our displacement equation looks really messy right now. Can we try simplifying this a little bit first? Whenever we have brackets, if we can, try and expand them. Make it a little bit easier first.
Would Laurel Jones please come?
160 times a quarter makes 40t, and then 160, and then 160e to the negative 1/4 t. You're going to say, well, why would you do that and have these extra parts? Remember, my objective is to take a derivative. It's easy to take a derivative in parts. The derivative of 40t is just 40. The derivative of the 160 part, well, that's just 0. And then the derivative of the last piece, well, it's an e expression. So 160e to the negative t over 4 times the derivative of the exponent, which is negative 1/4. Now, you might have noticed I kind of cheated here. I took the 1/4 t and I turned it into a t over 4. That is exactly the same thing, right? This means that. It might be a little bit easier to work with it in the fractional form. Okay, let's simplify our expression for velocity here. We'll get 40 plus, let's multiply together the number and the number. Oh, it's not even a plus anymore, right? It's going to be a minus now. 40 e to the negative t over 4. Here's our velocity. Starts off at 40 and it goes down from there. Okay, part B. What do we have to do in part B? Show that the acceleration is given by 10 minus 1/4 v. Acceleration. What do we know about acceleration? Well, we know acceleration is the derivative of velocity. Oops, that's all messy there. I'll fix that. So let's find the derivative of velocity. Derivative of 40, gone. The derivative of this piece, negative 40 e to the negative t over 4 times derivative of the exponent, negative 1/4. Again, we'll simplify it, number times number, and we'll end up with 10 and e to the negative 10 over t over 4. Now, that's not quite what they have there. They said 10, all right, but they said minus 1/4 v. They said a is supposed to equal, a equals 10 minus 1/4 v. Well, where did that come from? Let's give it a try. What is v? V, we said.
Wood Laurel Jones.
We said v was all of this. So let's put that in for v. 40 minus 40 e to the negative t over 4. And let's see what happens. Can we show that? Okay, 1/4 times 40, that's minus 10. One up here, that would be plus 10 e to the negative t over 4. And 10 minus 10 makes 0, so I get, hey, isn't that kind of the expression we already had for acceleration? That one and this one. So we've shown true. They just did a different version from us. Okay, but our acceleration is 10 minus 1/4 times the velocity. I need this working with derivatives. Okay, part C. Find the terminal velocity of the skydiver by determining the horizontal asymptote. And just an aside for you, terminal velocity is the constant velocity attained when air resistance balances the force of gravity. What does that mean? Well, that means we start at this speed and eventually we level off. You can only fall at a certain speed. It's called the terminal velocity. It's as fast as it ever gets. Okay, so to do this, we need to figure out, they give us a hint here, horizontal asymptote. How do we find horizontal asymptotes? Well, we do that by figuring out the limit as we approach infinity. Oh, sorry, not h. As time approaches infinity for our function. Which function? We're looking at the velocity function. So I need to figure out what happens when I put a really, really big number into my derivative for velocity. So derivative for velocity, just to point it out again, is the limit of t approaches infinity. That's a really messy infinity. For 40 minus 40 e negative t over 4. So what would we get here? We'd get, if we put a really big number in, 40 minus 40 e to the negative infinity over 4. Well, what is that going to do? That's going to give us 40 over e, make it a positive exponent, like that, right? So e to a really big number. Think of a really, really big number you can put as an exponent. What's going to happen there? We're going to get 40 minus 40 over a really, really giant number now. And what's 40 divided by a really, really giant number? A really, really small number. So basically, we get 40. That's our end behavior. Our horizontal asymptote would be y equals 40. Okay, that's the speed we approach. Okay, last part. At what time is the velocity 95% of the terminal velocity, and how far have they fallen? Okay, so part D. I want to figure out when do we hit 95% of terminal velocity, in other words, of 40 meters a second. So 95% of 40, 38. So when does our velocity hit this? Okay, so what do we know? We know our velocity equation, negative t over 4. That's come out to 38. We want to solve this. To solve it, okay, we got to create a base on each side. Then we can use our log law idea. Okay, so we're going to rearrange. We're going to divide out both sides by this negative 40, which is 1/20th, or 0.05. That's fine too. Don't really make a difference. Okay, and then we're going to take the ln of each side. So the ln of 1/20, I'm going to change to a decimal, okay, 0.05, and the ln of e to the negative t over 4. Well, we know based on the fact that it's a log law, my exponent can come down in front, and I can put it like this. But I also mentioned that the ln of e always equals 1. So I don't really need this piece anymore. So in other words, the ln of 0.04 equals negative t over 4. Or if I want to solve for t, okay, t could be the negative ln of 0.05. Okay, let's change sides here to make it look a little bit easier. Get rid of that negative sign. And again, get rid of that 4 by putting it out front. And that's something I can punch into my calculator. If you punch that into your calculator, negative 4 ln of 0.05, you should get 11.98. Okay, so it takes us almost 12 seconds to reach 95% of terminal velocity. The other part to that question says, how far have they fallen at that point? In other words, what is their distance or displacement at that point? Which means we need to go all the way back up to the question, okay, and replace time with 11.98. So our question was, we had 40 t, oh, t is 11.98, okay, minus 160, I'm using the simplified version, okay, plus 160 e to the negative 11.98 over 4. If you punch that all into your calculator one time, you should end up with approximately 327.3 meters. Okay, so that's an introduction of how we can use E, what E is, continuous growth or decay, how we can take derivatives, and how we can apply derivatives and solve things using the inverse of E, the natural log, which we call ln. Okay, homework questions you should try, a couple of them. Make sure you can do some ln stuff. We'll look at the other kinds of exponential equations tomorrow.